Okay, guys, so I'm gonna quickly run through the answer, right? So what we have here is the mass spring damper system that we discussed in the beginning, right? So you have the ABCD equations, right? And those equations are given to you in those notes. So we derived them ourselves before, and so they basically look like this, right? This is our A matrix, our B matrix, and a C matrix, right? So how you would write that out is basically they've told you what these parameters are, the K and the M and the C's, right? So in this question, they've said that M is equal to 1000 kilograms, K is 50 kilograms per square seconds, C is 20, and so on, right? So what you do is you define those values M, K, C as 100, 50, and 20, and then you basically write out the matrix form, right? And so the matrices are 0, 1 minus K over M minus C over M, basically these, right? Also, by the way, usually the state space model also has this additional term called df, right? But in a lot of cases this d is 0, right? Which is why I didn't write it, but usually you write d equals 0 as well, right? So when you're defining using this function in MATLAB state space, you kind of need to put d equals 0 also, because that's how it works, right? So you define the matrices, and what you do is you use this function called SS, right? That's state space, and all you have to do is input these values, A, B, C, D values, and it'll give you your state space model, right? So that's super easy. And then what I've asked you guys to do is use what you call the step response of the open loop system using the step function. So if you go here, what a step response is, so basically remember our diagram here, right? A step response is what if your input was a sudden jump like this with a value of 1. What will the output look like, right? So the reason we look at something called the step response is, let's say you want to just look at how the system behaves, right? Your input in the real situation could be anything, right? You could be giving any sort of input to your system. But let's say you just want a standard way of testing your system, right? So what we usually use to test our system is this thing called the step response. That is, if you give a sudden input like this, what's going to happen, right? So in the spring damper system, for example, what that means is, what if I suddenly give a force, right, of 1 Newton and sustain it for a while? How is this system going to behave, right? So by looking at that step response, you can kind of get an idea of how the system overall behaves, right? Whether the system is stable, whether it's not, and so on, right? So MATLAB offers this thing called step, which just does a simple step response, right? It just adds, just gives an input of something that looks like this, of 1, right? So this is called a step input. So it gives a 1 Newton force, right? So our U, or in this case F, right, our external force is 1 Newton. We suddenly put 1 Newton in there, and we look at what happens. So if I run this, I get what the output looks like. So here you can see this is what the output looks like, right? It oscillates and then comes down to a steady state value, right? So what that means is, if you have a spring damper system here, right? How do I delete all this? Right? Imagine I suddenly give it a 1 Newton force like this, right? I suddenly give it a 1 Newton force, and I keep giving the 1 Newton force continuously, right? So what's going to happen is this thing is going to oscillate, right? it's going to oscillate, and it's going to come down to and stay at a certain value depending on this K and C and mass values, right? So looking at this, and our output is this displacement. Looking at this, what has happened? It has oscillated to about 3 centimeters, right? This is in meters, and then stopped at about 2 centimeters. So it has oscillated and stopped around here, right? If I'm giving it a constant 1 Newton force, right? So that's what the open loop system is. This is how the open loop system behaves, right? So this final value that it settles down is called the steady state value, right? And you can see that it oscillates and comes down to this steady state value, right? So if the system suddenly gets a step force, this is how it will behave, right? This is a completely open loop system, and this is how it behaves. Any questions? Nope. Okay, so now we're going to do pole placement, right? So according to this question, right, you're supposed to place the poles at -0.1 and -0.3, right? So before that, what I'm going to do is I'm going to actually look at the current poles of this system. How will I look at the current poles of this system? I can look at its eigenvalues. Can someone predict what the eigenvalues will look like before we even run it, judging from the step response?
It would be negative because it's
correct
moving towards stability.
And it will have complex values, right, because it has an oscillation. So if I run this, can you see these are the eigenvalues? They are both, the real components are both negative, right, because it's stable, but it's oscillatory, right? It has complex values. Cool. So what we're going to do in 2.5 is we are going to place the poles at -0.1 and -0.3. That is without the complex values, right? And so the question is, how do you place these poles? Like, what is the K matrix that we need to use to place these poles? So in MATLAB, it's super easy, right? You didn't have to do all that work that we did before, right? Look at how much work that is, right? We can just use this single line called place. So how you do that is you first mention what are the poles you want. So according to this question, the poles that we want are, the poles that we want are -0.1 and 0.3, right? So I'm going to put that into a vector called P. And basically what you need to do to place the poles is give your input matrix, your B matrix, and the poles that you want to place, right? And it will automatically calculate the K matrix for you, right? And now what we're going to do is we are going to look at, if we have this K matrix now, so for example, if I run this, right, just look at the code up to this point, okay? I've given the answer here also, forget about this stuff for now, right? So what I've done is I place the poles now at -0.1 and 0.3 and calculated the K matrix that I need to do that. So if I run this, I get this output. So our gain for K should look like this, -4720, right? So now that I have my K matrix, I can design my closed loop system, right? So what does my closed loop system look like? It will have a new A dash, right? Just call that A dash. Will be basically A minus B K, right? So my new closed loop system, right? So I'm going to call that spring damper closed loop, that's a long name, right, is going to be equal to SS. So I'm using the same function SS, but instead of A, right, I'm going to use A dash, right? Or I can just straight away even like just put in A minus BK here. Actually, I'll just do that so that you guys get the idea, right? Actually, I'll do it the other way because, yeah. So how does the SS function work? You put the A matrix, the B matrix, the C matrix, and the D matrix, right? So what changes when you add a closed loop system is your A matrix changes to A minus BK, So instead of A, our closed loop system will have a dash and then B, C, D. Okay. So that will be a closed loop system. Cool. So now let's look at the closed loop system's step response. Can someone suggest what it will look like?
It won't have oscillations.
It won't have, yes, and it will,
Exponentially degrade, like downward.
yes, right? So if I run this, remember it's a step response, right? So you're constantly giving it a force,
Okay.
right? So it will, like, the error will now exponentially decay, right, between the input and the output, and as a result what you'll get is it will now where was that, instead of going all over the place, it will now come to a stable response, right? So your spring damper system, again, if we connect this back to the system, now what will happen is if you give a constant force, it will, instead of oscillating and coming to, what was it, 0.02 or something, it's going to straight away, when you apply this force, because we've added a new controller here, it will end up somewhere else, right, and stay there, right? So where is that? Yeah, so you can see that it stops around 0.34, right? But remember, now we want to control this, right? We want it to come to where we want it to come to, right? So remember, in this example, we had a reference signal, right? We want it to come to that reference signal, right? So right now, what is our reference signal? It's the step input, right? It's going from 0 to 1, right? But you can see here, it's not stopping at 1. It's stopping somewhere, it's stopping at 0.34. But we want this to go like this and stop at 1, right? That's where we need to scale our input. So that's where this J comes in, right? So when we are giving this input, if we gave the input higher, okay, so if we, for example, want it to stop at 1, but it's stopping at 0.35, what we need to do is 1 has to be multiplied by another value to increase that value, so that this will actually stop where we want it to. Does that make sense? So we need to actually multiply the reference by a certain value. So you can think of it as multiplying the reference as a certain value, or multiplying this entire system's response by a gain value, right? So how you do that is in this step response function. So the problem is MATLAB step response function will always give 0 to 1, right? But for it to actually stop at 1, we need to give it 1 multiplied into something else, right? So this value that it stops at, this steady state value that it stops at, is called the DC gain of a system, right? So MATLAB helps us calculate this DC gain by using this function DC gain, right? So if I say DC gain and give this value spring, give the state space value of the closed loop system and run this, you can see that the DC gain is 0.3333, right? So this value is not 0.34, it's 0.3333, right? So if you can multiply the input by 0.333, you will get the answer that you want, right? Because this is what do you call it? So how will I do that? Yeah, so think of it as just like kind of scaling the system, right? So that it now responds the way you actually want it to, right? So you have the DC gain of the current system, you take that 0.33, and if you multiply the system by 0.33, hold on, do you multiply or do you add? Yeah, just give me a minute to think about it.
If you multiply, it will reduce it further, no?
Yeah. You have to divide it by
Divide
0.33.
it.
Yeah, so now it actually responds to 1. So our input is 1, right? So our reference signal here is now 1, right? And our output is also 1, right? So for example, if you give it so this is the advantage of testing with the step input, right? Think of the AC situation again, right? Imagine this was not the spring mass system, this was your AC, and you're saying 20 Celsius. I want this at 20 Celsius, right? We now know that if I give it 1 Celsius, your output will end up at 1 Celsius, right? In this, not in a step way, it's actually, yeah, if I give a sudden 1 Celsius change, you know that it will go like this and somehow end up at 1 Celsius now, right? Because you've adjusted this K and these J values in a way that it will nicely come to 1 Celsius. Before, what was it like? It was going like this and ending up at 0.02 Celsius or something, right? But now you've adjusted it in a way, you adjusted these K values and these J values so that it ultimately now comes to 1 Celsius. So if you give it a step input of 1 Celsius and it comes to 1 Celsius, even if you give it a step input at 20 Celsius, it's going to go to 20 Celsius, right? Because it's just a scaling of the input now that's happening. Is that clear? So what you've essentially done in this question is you created a spring mass system that allows you to place it anywhere you want, like you place this mass anywhere you want it to go to, right? So it will now get your displacement to where you want it to go to. So here the displacement now ends up at, your output ends up at 1 meter, right? You give it an input value of 1, right? So the input value is not force anymore, right? It's some sort of reference signal, right? And sorry, it is a force ultimately, right? But for you to get 1, now it knows how much of a force it needs to give you, so your output becomes 1, right? So you created a system in a way where if you give it a force of 1, it will output a displacement of 1. Cool. Okay, so we've used MATLAB's tools to quickly and easily kind of do that. All right, so that is question 2 done. Any questions before we jump into? So now, for example, in your projects, if you want your robot to go to a certain place, if you can write the system's equations of your robots, like how the velocity of your robot connects to the motor speeds of your robot or something like that, you can now, for example, tell the robot to go where to some place, and you can control it so that it goes there without oscillating. Otherwise, for example, the robot will go like this and come back, or whatever. You can get the robot to nicely stop at a certain place. Any questions? So everything ultimately depends on these models, right? Your A, B, C, D equations. So how much detail you want in those A, B, C, D equations depends on the physics and depends on the level at which you want to control it, right? Okay, so now we're going to start a new section called LQR control, right? So we learned pole placement, right? Now we're going to learn LQR control. Do you guys want to take a small break or something before, or are you guys okay? Am I like covering too much?
Um, yeah, we could take a break, but before that, that SS function,
Yes.
like when I tried to run on MATLAB, it says it requires one of the following, like control system toolbox.
Oh yeah, you have to install the control system
Yeah.
toolbox. Yeah.
Like this happened, like similar thing happened last class also. So,
Okay.
like before the class, if you can just tell us during the pre-work, like which toolbox is required
Okay, sure,
to
sure.
download it. Like,
Yeah,
because when you download it in class, like
it takes
I
time.
think,
Yeah.
yeah.
Yeah. Okay. Yeah, I apologize for that. Yeah, it's because I think I have all of these installed default on MATLAB, so I don't realize that some of the time you have to install it. But yeah, thanks for the suggestion. Next time I'll. So these are the toolboxes you generally need. You need the robotics systems toolbox to do all the ROS stuff. You need the computer vision toolbox to do all the image processing, computer vision stuff, and the image processing toolbox. And you need the control systems toolbox. That's pretty much it. What I'll do is I'll make a list of those and I'll put them on Canvas. So it's really like 4 toolboxes that you need. And yeah.
Yeah, that's good.
Okay, sorry about that. All right, so I'll give you guys like 5 minutes just to take a breather because I realize this is a lot of material. So take like 5 minutes and then I'll discuss the LQR control stuff. Cool?